Question 12. So X is a group 2 metal. I think these days they no longer use this Roman numeral. They'll do this Latin number, group 2 metal like that in your periodic table. So this carbonate of X decomposes when you heat it in a Bunsen burner flame to give you carbon dioxide and white solid residue. If it is a group 2 carbonate, you know group 2 carbonate, it will give you the group 2 oxide. There's M2 plus CO3 2 minus. They'll give you the M2 plus and O2 minus like that. And they'll also give you CO2 gas. This white solid residue is your group 2 metal oxide. Now this thing is sparingly soluble. Sparingly means not very soluble in water. Even when a large amount of solid residue added to water, the pH is less than that of lime water. Less than that of lime water. What do we know of lime water? Lime water is actually saturated calcium hydroxide. So this is about your solubility of the group 2 hydroxide. So we know that going down the group 2, the solubility of the group 2 hydroxide would increase. Does it increase linearly like this? I don't know and I don't care, because all I care about is barium hydroxide is very soluble, it's around pH 14, whereas magnesium hydroxide is not very soluble, it's only around pH 9. This is what you get when MgO tries to dissolve itself in water. Lime water is here. So this is your lime water. It is your saturated calcium hydroxide there. So this one, it says the pH of the saturated solution is less than that of lime water. So this is lower pH than that of lime water, and therefore it is not as soluble as lime water. So this is less soluble than lime water. If you are less soluble than lime water, that means you have lesser hydroxide in the solution, because not very soluble, and therefore your pH will be lower value than that of the lime water, which means we are looking at this solid residue being magnesium oxide, because magnesium oxide dissolves in water to give you magnesium hydroxide. Although not very soluble, it is going to have a pH lesser than the pH of the lime water solution, because it is less soluble than the lime water. So that means we are looking at this being MgO. If that is MgO, we are looking at this being MgCO3. So the metal itself is going to be magnesium, and that will follow this particular trend as stated in the question there. Question 13, rat poison needs to be insoluble in rainwater. So this is insoluble in water, whether it's rainwater or not, it's going to be insoluble in water, but soluble at the low pH of the stomach content. So this is acidic in the stomach. So what is a suitable barium compound to use for rat poison? If we look at barium hydroxide, this is not going to be suitable because this is very soluble in water. Based on what I just explained in the earlier question, this is around pH 14. You gotta be soluble at low pH in the stomach content. This is barium sulfate. It is a white precipitate. This is a salt. It's insoluble in water. This one does not react with acid. Okay, it doesn't react with acid at all because it's already a salt that is formed from the sulfuric acid itself. Okay, so that thing is not going to be suitable. Now between these two, barium chloride is soluble. This is in fact what you use, aqueous barium chloride, or you use aqueous barium nitrate, and this is what you use to test for sulfate in the lab. Sulfate versus the sulfite. These are part of your paper 3 practical studies, and you must have done this as part of your paper 3 practical studies because there is no exemptions to practicals in A level at all. So you will know that these are what you use. These are very soluble in water. You're looking for something which is insoluble in water. Barium carbonate, all the group 2 carbonates are insoluble in water. That is from GCSE all level or IGCSE level. And it can react with the acid in the stomach because all the carbonate can react with acid. So CO3 2 minus can react with acid. This is the test for carbonate. Put any acid to it, you get effervescence as a result of the carbon dioxide being formed. And you can test the carbon dioxide with lime water that will go milky or cloudy. Question 14, so what we're looking at, we have these elements of the third period chemistry, so sodium all the way to chlorine. We're looking at ionization energy. So this one is say has a lower first ionization energy than the preceding element. Preceding means the one before or the one which is previous. Okay, proceeding is after. Okay, whereas preceding, pre means before or the previous thing. Okay, so this is first ionization energy. We know that across a period it will rise up, it will drop down, it will rise up, it will drop down, it will rise up, and it will go all the way down there. So we know that in terms of the position, this is your group 1 metal. So there is going to be sodium. The height there is magnesium, and then from magnesium to aluminium, you have the filling of the p subshell. So when you're removing from the p subshell, it's further away, more shielded compared to the electron in the s subshell, slightly easier to remove. Between the second drop, so in between this second drop, in the first ionization energy, you have the group 15 and the group 16, which across the third period, that is going to be phosphorus and sulfur. This is to do with the P3 versus the P4 repulsion. So you got to pair them up. These paired electrons, they repel more than the unpaired electrons, slightly easier to remove the unfavorable repulsion. Then they rise all the way up to the noble gases. There are argon there. And then when you reach to argon, the next element comes from a new shell further away from the nucleus. That's going to be potassium, more shielded, and therefore much easier to remove compared to sodium. Now, lower first ionization energy than the preceding element, conducts electricity. Conducts electricity means not non-metal, not the non-metal. So from the option given, we can cross out phosphorus and sulfur because of conductivity. Now, in terms of lower atomic radius, so we're going to know the trend in the atomic radius as well. So across a period, in general, your nuclear charge increases. Your shielding is roughly constant because you are filling in the same shell. So overall effect across a period is that your net nuclear charge will increase, and therefore your size, your atomic radii will decrease, going from sodium all the way to chlorine. What you might not realize is the argon. If you have a periodic table, not a periodic table, if you have the data booklet, you will see that argon has a bigger atomic radii than sodium even, which is why they don't ask you to put in argon in there, and which is why I don't put in argon in my atomic radii trend at all. Okay, sodium all the way to chlorine. So that is to do with atomic radii. So this one has a lower atomic radius than the preceding element, aluminium and magnesium. So if we look at aluminium and magnesium, so if magnesium is there, aluminium is there, you're looking at lower atomic radii than the preceding element. Magnesium has a lower one than sodium, aluminium has a lower one than magnesium, so both of them could be the answer based on lower atomic radius. Doesn't tell me anything. I have to look at the first ionization energy. If you look at the first ionization energy, magnesium has a higher first ionization energy compared to the one before. So magnesium has a higher first ionization energy than sodium. You're looking for a lower first ionization energy than the one before. Aluminium has a lower first ionization energy than the element before it. So aluminium is the answer and not magnesium there. Okay. Question 15, this is about the melting point of the period 3 elements. So going from sodium, magnesium to aluminium, we know that these are giant metallic structure. So even year 9 chemistry student will be able to tell you about structure, and therefore you need to break the strong metallic bond. So what exactly is the metallic bond? There are 3 factors that affect your metallic bond. This is something that you would have come across when you were in year 9, for instance. Okay, we know that we don't have negative ions. Instead, what we have is these delocalized valence electrons, the sea of delocalized valence electrons that come from the metal atom having delocalized the outer shell electrons. These happen to be the metal cations that are formed as a result of the atom, shedding off or losing off the delocalized all your valence electrons. As you go from sodium to magnesium to aluminium, we can imagine that we have more valence electrons to be delocalized. So we are pumping in more and more electrons into the delocalizations, and therefore we increase the amount of negative charge there is in the system. As we do that, our cations also increase in charge. So the cationic charge increases. So meaning to say your cation go from Na plus to Mg2 plus to Al3 plus. And similarly, going from sodium all the way to aluminium, if you have Na plus, Mg2 plus, and Al3 plus, if you do a quick counting, protons, electrons counting, you will see that they have the same number of electrons, But then what happened is same number of electrons, greater number of protons, you develop a stronger effective nuclear charge between the electrons and the proton. They get pulled closer together. In terms of the radius, the sodium plus is going to be bigger than Mg2 plus, is going to be bigger than Al3 plus. So we can say in general, the charge density of the cations, bigger charge, smaller size. So the charge density of the cations is getting higher. So the cations are getting higher in charge density. There are more electrons that come from the group 3 or group 13 versus the group 2 versus the group 1 metal. So that means the metallic bond gets stronger in that extent. So in terms of the three factors, so we are just looking for anything that result in this increase in melting point that come from these three particular factors that contribute to the strong metallic bond there. Okay, changes in first ionization energy, that has got nothing to do with this thing here, I think. Increase in electronegativity, that has got nothing to do with what I just explained. Increase in the AR, again, this has got nothing to do with van der Waals forces because these are metals. We don't talk about molecule, we don't talk about van der Waals forces, we don't look at the AR of the elements. So the next thing is increase in the number of outer electrons, that's to do with the valence electrons. So that means D is actually our answer that we're looking for because there was one of the factors that I discussed there. The more electrons you pump into this sea of delocalized valence electrons, the stronger is the attraction between these electrons and the cations, therefore stronger metallic bond, therefore the melting point increases there. Question 16. So we have an oxide of a period 3 elements. This reacts with water to give an acidic solution. So your first hint there really is these are oxide. So these are coming from oxide of the element reacting with water. So we're looking for acidic oxide. If we're looking for acidic oxide, so MgO is out because this thing is what you call basic oxide. We can cross out Al2O3 even though this is amphoteric because of this thing. It reacts with water because this thing is insoluble. Al2O3 together with SiO2 is insoluble in water. Okay, in doing so, I'm left between C and D. So I need to think about these questions. So I have X and this oxide when I reacts with water. So what do I get? P4O10 plus water will actually give me H3PO4. If you work out the oxidation number, you will know that this is phosphorus plus 5 and this is also phosphorus plus 5 as well. You don't get the H3PO3 because there will be phosphorus plus 3 that will come from P4O6. Balancing equation is very important. I'll have 4 of that and I'll have 6 of water there, and that should give me 6 oxygen plus 10 oxygen, 16 oxygen on the right hand side there. So assuming, I just need to check for one, assuming this is what we're looking for, if this is what we're looking for, C is the answer. If this is not what we're looking for, we just cross this out, that means D is the answer without wasting any more time. In terms of the acid, this is how much sodium hydroxide is required to neutralize that. So we're given the mass of X. So the first thing I should do really is to work out the MR of P4O10. So from your periodic table, so where is your periodic table? So I have a look at phosphorus. I think it's 31.0 plus, times 4. 31.0 times 4 plus 16.0 times 10. I get 284. I only need to check for one, right? Remember, if this is the answer, I will get this to match the mole of the sodium hydroxide that reacts if I have a balanced equation. So looking at that, and then if I have 0.100 gram over 284, so how many mole of this phosphoric acid will I get? I will get 4 times. I will get 4 times the mole of the P4O10 because 1 mole of this gives me 4 times the acid. So the acid that I get from reacting this much is going to be 4 times that. So 4 times 0.100 divided by 284. I get an answer which is 1.41 times 10 to the minus 3 mole. The next thing I need to do is to get the balance equation for the H3PO4 plus NaOH. So this one will give me Na3 P of 4 because I have Na plus and P of 4 3 minus. Just like I have H plus and P of 4 3 minus, Na plus P of 4 3 minus. As you would know, exchanging the valency, that means you need 3 of the Na plus and 1 of the P of 4 3 minus. And of course I have water as well. Balancing equation, very, very important in this question. 3 of the NaOH, then I'll get 3 H2O as a result as well. So what I get here is this one. I have the mole of this. So the mole of NaOH is going to be 3 times the mole of the H3P of 4. So what do I get? So 3 times my previous answer. I get 4.23 times 10 to the minus 3 mole. So this is how much NaOH is required to react with all of the H3P of 4. That doesn't look like the actual mole of NaOH required, but let's have a look at this. So the actual mole of NaOH required will be N equal to C times V. So the C is in mole per dm cube. The V is in cm cube. So convert that to dm cube. So 0.100 times 25.0 times 10 to the minus 3. I get 2.5 times 10 to the minus 3. So this is actually reacted. But if you have this much 0.100 gram of this, which has this MR, you're gonna get 4 times this much acid, and all the acid is gonna give you 3 times as much NaOH that's required. This is how much actually reacted. This is what you calculated to be what would react if you have 0.100 gram of these. They don't match. The mole of the NaOH don't match. What you put in and what you expect to react doesn't match. So C is not the answer. D must be the answer. I leave it as an exercise for you to actually, confirm that D will be the answer. You write the equations. SO3 plus H2O will give you H2SO4. H2SO4 is a sulfate. So the sulfuric acid plus the NaOH will give you sodium sulfate, and you can do the exact same calculation and convince yourself that D is the answer. Question 17. Which statement about bromine is correct? So bromine is insoluble in nonpolar solvent. That is wrong. It's actually soluble because nonpolar likes to dissolve in nonpolar stuff. As you can see, they are equal electron negativity. Therefore, bromine is nonpolar, nonpolar dissolve nonpolar, polar dissolve polar. So A is wrong. Bromine vapor is more dense than air. We can imagine that bromine molecule being further down in the periodic table, they have quite heavy relative atomic mass. Compared with air, we only have nitrogens and oxygens. They are fairly light in comparison with the MR of bromine. So perhaps B is correct, but let us just go through C and D first. I can tell you D is wrong. So the one which is purple is actually going to be iodine. So I2 gas is actually purple vapor. In terms of bromine, it's a reddish brown liquid, but when it vaporizes, it's going to be like a reddish brown vapor as well. It is not going to be purple as well, but naturally at room temperature and pressure, it's a reddish brown liquid. Now part C, bromine will not vaporize significantly under normal conditions. This is actually wrong because it will vaporize quite significantly as well. I mean, okay, if it has quite low boiling point, so it's quite easy to vaporize. So B is actually going to be the best answer instead of C there. In this question 18, so we have some aqueous silver nitrate, which is used typically to test for some halide. In this case, we have some aqueous barium chloride. So obviously you have some chloride there. So the first reaction there, the Ag plus from the silver nitrate aqueous will react with the chloride from the barium chloride aqueous and give you this AgCl solid. This is your white color precipitate, a classic precipitation reaction. But when you add excess dilute ammonia, you know that silver chloride will dissolve in excess ammonia in this equilibrium reaction to give you this colorless solution. So it's a silver diamine complex. So you'll learn more about this in A2 transition metal. This is going to be aqueous, and this is plus Cl minus aqueous. Aqueous and aqueous there, that is your colorless solution, because the white precipitate will dissolve in excess ammonia to give you a colorless solution. Now, when you add some excess dilute nitric acid to this, it produces you back the white precipitate, because you can imagine, what does the nitric acid do? The nitric acid is a source of H+, it will react with ammonia, and what it does is, it will give you ammonium. So it will form these neutralizations, it will form this salt, the ammonium salt, it will remove, so the acid will remove the ammonia, acid will neutralizes the ammonia. So as you neutralizes the ammonia, what happened is you would precipitate out a white precipitate again, because as you remove the ammonia, what is left behind is the Ag plus and the Cl minus, which is going to combine together to give you more of the AgCl precipitate. So what is Z? Z there is still going to be the white precipitate, which means you're going to get back the AgCl precipitate. Question 19, you have element X, which produces this pollutant oxide. Y can be further oxidized to Z. Two students made the following statements. The molecule of Y contains lone pair of electrons. And then student Q said the oxidation number of X increases by 1, going from Y to Z. So we can be thinking about this element X that give you this pollutant. In the context of, well, they say it could be carbon, could be nitrogen, or could be sulfur. So we're not just thinking about nitrogen or sulfur as in the syllabus, but also in terms of carbon. Let's think, if you are an oxide that can be further oxidized, such as CO, it can be further oxidized by gaining oxygen to give you CO2. So yeah, that is fine there. There's carbon plus 2 oxidation number, as the oxygen is minus 2 oxidation number. The carbon there is plus 4. The whole compound has 0 oxidation number. Carbon plus 2 times minus 2 for each of the oxygen is minus 2 in a compound there. So this is an increase in oxidation number by 2. So can't be carbon there. How about nitrogen dioxide? Same deal, I guess. So half there. Nitrogen plus 2. Nitrogen plus 4. Again, an increase in oxidation number by 2. SO2 plus a half O2 give you SO3. This is the same deal, sulfur plus 4 going to sulfur plus 6 oxidation number there. So student Q is definitely correct in terms of, student Q is definitely wrong for all of them. For carbon, nitrogen, sulfur, all of them increase in oxidation number by 2 and not by 1. So that means student Q is wrong, Q is wrong, Q is wrong. So B and C is out. But is student P correct? The molecule of Y contains lone pair of electrons. If you look at all of these, CO basically looks like this. You have lone pair of electrons on both the carbon and the oxygen. Sulfur dioxide looks like this. You have lone pair on the sulfur, where this one is 120-degree bent shape. So definitely both of them will have a lone pair of electrons. If you look at NO, NO is a strange one because it actually looks like that. So you have a lone pair on the nitrogen, but you have a single electron on the nitrogen as well, which is unpaired electron. That's why they say NO is a radical. In fact, someone won a Nobel Prize. I think it was a physical chemist who won a Nobel Prize for his or their work. I'm not entirely sure. I forgot already the name of the person, but it was all about NO chemistry being a radical. So, instead of it just being radical, it does have lone pairs. So the molecule of Y contains lone pair of electrons. All of them have lone pair of electrons. So the P is definitely correct. So, D is definitely wrong because it's saying that P is wrong. Q is wrong, P is correct. Question 20, how many isomeric esters have this molecular formula of 4 carbon? So a 4 carbon ester. So if you think about question 20, 4 carbon ester. So how about 1 plus 3 in terms of your ester? So you have ester like this, R and R dash. If I split them up like that, you can hopefully see that this is the carboxylic acid fragment, which includes 1 carbon of that carbonyl fragment there. And of course, you have your alcohol fragment on the right hand side as shown there. So when I say 1 plus 3, I meant 1 of that carboxylic acid, so that if I draw my skeletal formula, they will look like that. So there's 1 carbon for the carbonyl carbon there, carboxylic acid there, and then I will have 3 carbons on the alcohol, such as 1, 2, and 3. Plus 1, 4. There's one hydrogen, there is two hydrogen, three hydrogen. Skeletal formula, the fastest way you can do this kind of isomers kind of question. All right, so make sure you can do skeletal formula. So that is your first one. But then when you think about your straight chain here, 1, 2, and 3, you have 3 carbon in a straight chain. You can definitely branch them out into this isomer. Okay, so this is a straight chain and this is a branch chain. Both of these are called chain isomer under structural isomer. So both of them are 1 plus 3, and then I can do 2 plus 2, so meaning 2 carbon on the carboxylic acid, 2 carbon on the alcohol, 2 carbon on the carboxylic acid, 2 carbon on the alcohol. Last but not least, I can be thinking about my other one, which is 3 plus 1. So 3 plus 1 there would mean that my carbonyl there, my carboxylic acid, 3 carbons, 1, 2, and 3 carbons, and then I cannot have an OH because there will be carboxylic acids. I just have 1 carbon there. This is methyl propanoate. This is ethyl ethanoate. This is propyl methanoate. This is an isopropyl because it's an isomer of propyl. They call it isopropyl methanoate there. Okay, so there are 4 isomeric esters with that molecular formula of 4 carbon ester there. Question 21, you are looking at which skeletal formula represents a structural isomer. So in the context of this, they are all having the same functional group. So we know that there are 3 different types of structural isomer, one of which is functional group, which in this case is not going to be true because all of them have the same functional group of alkane. We also know that we could have a chain isomer. So chain isomer basically means straight chain versus branch chain. That was what we had discussed previously with these isomer 1 and isomer 2 for this isomeric ester shown there. Of course, the other one would be the position isomer. So where you switch their position around. So the first thing I'll do with this kind of question is find the longest chain carbon. If I label this 1, 2, 3, 4, 5, 6, 7, 8, 9 like that, I could go the other way around. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9. If I do the green color coding, so where are my branch? My branch would be at 2, 3, 5, 7, 8. 2, 3, 5, 7, 8. How about when I do the blue color one? So you gotta have the smallest number, right? So this one will be 2, 3, 2, 3, 5, 7, and 8. 2, 3, 5, 7, and 8. So as you could see, they have the exact same positions of the branch group there, so it doesn't really matter. So what I'm going to do now for this molecule A to D is I'm going to find the longest chain carbon. Okay, that's my first job. Find the longest chain carbon. 4, 5, 6, 7, 8, 9. 8, 9 or 8, 9 is the same thing there. So where is my branch? Is at 2, 3, 5, 7, and 8, and all of them have 1, 2, 3, 4, 5. All of them are CH3, just like that. If all of these are CH3 and they are at the exact same position, 2, 3, 5, 7, and 8, so that means these are exactly the same. It's not an isomer, it's exactly the same as the question presented. That is just shown slightly differently, but they're exactly the same if you count the carbons. Okay, option B, so 1, 2, 3, 4, 5, 6, 7, 8. So you could see is 8 carbon the longest chain now. If I start from here, 1, 2, 3, 4, 5, 6, not the longest. 1, 2, 3, 4, 5, 6, 7, 8. 8 is the longest. What else can I say? I have 9 carbon in the long chain, and then I have 10, 11, 12, 13, 14, like that. So I have 14 carbon altogether. 14 carbon total. 9 in the straight chain, 5 in the... Am I correct? So 9 is a straight chain, and then 1, 2, 3, 4, 5. 9 plus 5. 9 plus 5 is 14. Yeah, so there's 14 carbon altogether. I have 8 carbon here. And then I have 9, 10, 11, 12, 13. So I have 13 carbon total here. You're talking about isomer. Molecules that have the same structural isomers, molecules or compounds that have the same molecular formula. They already have different number of carbon. How can they be isomer to begin with? Okay, so that's how I can rule that one out. How about the next one? 1, 2, 3, 4, 5, 6, 7. I could go from this way around. 1, 2, 3, 1, 2, 3. That will give me the exact same result. Again, I'm going to count the total number of carbon first. So I have on the branch chain, I have 1, 2, 3, 4, 5, 6, 7. 7 plus 7 is 14, so here is 14 carbon total. That is not too bad. Let me just do the next one anyway. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Why in the world did I not start from here? If I start from here, I'll just have 1, 2. Whereas if I start from here, it's 1, 2, 3, 1, 2, 3. I want the longest chain carbon whenever I name my compound there. So I have a branch there. So 1, 2, 3, 4, 5. So 5 plus 9 is 14 carbon. So this one is okay. I have a CH3 at position 2, 3, 5, 7, and also 8. It seems like these are the exact same position as this one, 2, 3, 5, 7, 8. So this is the same as that. And because this is the same as that, this is the same as that. So D cannot be the answer, which means C must be the answer there. Okay, so I hope that makes sense to you. Why C is the answer and not D and not A, because these two are exactly the same as this question. This cannot be the answer because of 13 carbon total there. Count it for yourself.